Hello friends, now we will see one university question on plate girder design. This is for Anna University for the year November 2016. Span of that plate girder is 25 meters, is laterally supported, and the UDL on the plate girder is 80 kilonewton meter. This is in addition to its own self height. Now we have to design the plate girder without intermediate stiffness. Let us proceed with this design. We have to assume the self height because it is not included in the load, whatever has been specified. That is assumed as 8 kilonewton meter. Fy, the yield stress to be assumed for the design should be taken as 250 Newton per millimeter square. Total UDL is 80 kilonewton per meter, which is applied on the plate girder, plus the self height. Total weight is 88 kilonewton meter. The bending moment is 88 into 1.5. 1.5 is the load factor to be applied on the loads into L square by 8, 25 square by 8. Bending moment is equal to 10,313 kilonewton meter. Let us assume the total depth of the plate girder as 2000 millimeter. This has to be assumed in the range of span by 12 or something. This is just an approximation. Sometimes you can assume 1.5 meter, 2 meter, depending upon the span as well as the magnitude of the load. Here we have assumed the depth of the plate girder as 2000 meter. Now we have to fix the size and dimensions of flange and web of the plate girder approximately. For this, we can use this approximate formula. Area flange is equal to movement divided by total depth. To be precise, this should be the distance between the flange to flange. Suppose 2000 is the total depth. Center to center distance between the two flanges will be somewhere less than 2000. Nevertheless, we will go with 2 meter here because this is an approximation. So movement divided by this depth of the plate girder, which will act as a lever arm. Here again the approximation is center to center distance between the two flanges should be taken, but this being approximate, we are not bothered about the center to center distance of the flanges. Divided by Fy. Fy is 250. Material factor of safety is 250 divided by 1.1. Therefore, that 1.1 will go to the numerator. And then you increase this area by somewhere around 5%, just as an additional requirement. We are not sure whether this will cater to the actual requirement because this 2 meter is taken on the higher side. You increase this by another 5%, then you will get this. This is kilonewton meter and this is in meter. Therefore, we will get this in kilonewton. This kilonewton is converted into Newton by multiplying this by 10 power 3. Then you are having this 250 Newton per millimeter square. Therefore, you are getting this area in millimeter square. Now, let us provide 600 mm by 40 mm. That will be equal to 24,000 millimeter square as against the approximate calculation of 23,823 millimeter square. 600 by 40 mm. We should also ensure that the cantilever portion of the plate girder is less than the specified limit. Now, breadth is equal to the overhang portion of that flange is equal to 600 minus 16 by 2. This 292 mm is the overhanging portion of the cantilever portion of the flange. Divided by thickness of the flange, that is 40 mm. This is 7.3. Therefore, that is less than 9. Therefore, the flange is plastic. Now, what about the web? Web we can provide somewhere around 12 mm to 18 mm or 20 mm depending upon the magnitude of the load and span of the beam. Here we have assumed the web thickness as 16 mm. Here we have to assume it on the higher side only, because it has been specifically mentioned that we should not provide the stiffeners. If the web thickness is very low, then it will become slender and this web buckling will happen. For such thing, we have to provide the stiffeners. Here it has been mentioned specifically that stiffeners should not be provided. Therefore, the thickness has been assumed on the higher side, say 16 mm. Sometimes you can even go up to 18 mm or 20 millimeter. So this is. Now, what is D by T ratio? This 2000 is the total depth. Therefore, the clear distance between the flange to flange is 2000 minus 40 minus 40, that is equal to 1920. That is the depth of the web divided by thickness of the web, 16 mm, that is coming to 120. Now, this 120 is greater than the critical ratio of 67. This 67 will decide whether the web will buckle or not. If this is greater than 67, then the web will buckle. If web buckling is taking place, then we will ignore the web for calculation of moment of resistance. We will consider only the flange for calculation of moment of resistance, because this ratio D by T is greater than 67. If it is greater than 67, web buckling takes place. Therefore, web will not be considered for the calculation of moment of resistance. Now, ZP is equal to 2 times 600 into 40 into 980. 980 is the distance of the center line of the flange with respect to the neutral axis, that is with respect to the mid depth of the section. 2000 is the total depth, therefore this is 1000 mm. 40 mm is the thickness of the flange. Half the thickness is 20 mm. Therefore, distance between the center line of the flange to center of the section, that is mid depth of the section, is 980 mm. ZP is equal to area into X bar. There are two flanges. Two. Area 600 into 40. X bar is the distance of the area. That is equal to 980. So this is coming to 47 into 10 power 6 millimeter cube. This is ZP. Now we will check it for bending strength. MD, bending strength, is equal to Fy divided by material factor of safety into ZP, 250 Newton per millimeter square. Material factor of safety 1.1 into 47 into 10 power 6. This is coming in Newton millimeter. Divide this by 10 power 6, you will get it in kilonewton meter. The kilonewton meter, the bending moment is 10,682 kilonewton meter. This is greater than the calculated value of 10,313 kilonewton meter. So while calculating the area of the flange, in the approximate formula, you can have additional factor of 5% or 10% or 15%, so that you don't have to revise the calculations again. Here I have assumed only 5% over and above the calculated area, and the bending resistance is safe, and it is coming to 10,682 kilonewton meter, which is slightly higher than the calculated bending moment value of 10,313 kilonewton meter. Now we will check for shear strength of the plate girder. When stiffness are not provided, the value of kV should be taken as 5.35, and we have to calculate the shear stress. That shear stress in this case is equal to tau CR. Now, here I want to tell one thing. here D by T ratio is 120. Please remember, when the D by T ratio is 98, repeat, when D by T ratio is greater than 98, then the value of the shear stress tau B is equal to tau CR is equal to kV pi square E divided by 12 into 1 minus mu square into D by TW whole square. This holds good if D by T ratio is greater than 98. Please understand, tau B is not equal to tau CR for all the cases. Strictly speaking, we have to calculate tau CR. Based on this tau CR value, we have to calculate lambda W, and then we have to calculate tau B, which is the allowable shear stress. Tau B is a function of tau CR and lambda W. Here, after calculating the lambda W based on TCR, and you apply the formula for tau B, the shear stress, instead of in terms of tau CR and lambda W, you will get the same value as TCR. Hence, I am taking tau B is equal to tau CR. This is not mentioned in the code. Please understand, this is not mentioned in the code. Code says, based on tau CR, you calculate lambda W. Based on tau CR and lambda W, you calculate tau B, which will come to the same value of tau CR, that is 67 Newton per millimeter square. This I have observed holds good when T by T ratio is greater than 98. So tau B, allowable shear stress, has been calculated 67 Newton per millimeter square. Now shear strength VD is equal to the area, the actual shear force is equal to 88 kilonewton into 25 span. 1.5 is the load factor divided by 2, the reaction at one end. This is the load factor, UDL, load factor, span divided by 2, 1650 kilonewton. Shear strength is equal to 67 Newton per millimeter square, that is tau B, which we have calculated 67 divided by material factor of 1.1 into area resisting the shear, that is equal to 16 mm thickness of the web into 1920 depth of the web. This will come in Newton. Let us get it in kilonewton divided by 1 by 10 power 3. It is coming to 1871 kilonewton, which is greater than VU. Now, width of the bearing, let us assume somewhere around 400 mm. Width of the bearing is equal to 400 mm. Now, the contact here, the total bearing strength is equal to the contact area. Contact area is TW into BW plus 2.5 times TF. BW is the width of the bearing. TF is the thickness of the flange into 2.5. This is the contact area when it comes to mid depth with some 45-degree dispersion. So BW is the length of the bearing which is in the perpendicular direction. 400 mm is the dimension of the bearing in the perpendicular direction. So formula is BW, that is 400 mm, the length of the width of the bearing which is assumed, 2.5 times thickness of the flange, 2.5 times 40 into thickness of the web into 250 divided by material factor of safety. This will give in Newton. Divided this by 1 by 10 power 3. You will get the bearing strength in kilonewton. That is also greater than the shear force VU. Therefore, it is safe against bearing also. Here we have to design the section without stiffness. However, we have to provide some nominal stiffness at the support. That is mandatory. Only the intermediate stiffness you have the option to design with or without stiffness, depending upon the thickness of the web. but at the support location, you have to provide the bearing stiffener. Hence, provide nominal bearing stiffener, one number on either side, 12 mm thick stiffener. Now we have to check for deflection. The allowable deflection is L by 300. 25,000 mm is the total span divided by 383 mm. The load is W is equal to 88 kilonewton meter. Please understand, you should not apply load factor here. You have to check for deflection during the service loads. You should not apply the load factor. The formula is 5 by 384 WL power 4 divided by EI. 5 by 384. This is the load UDL in kilonewton meter into 25,000. That is millimeter WL power 4 divided by E into I. 2 into 10 power 5. And then moment of inertia. Moment of inertia is 2 into 600 into 40 into 980 millimeter square. 980 square. 600 into 40. This is A1 into H1. H1 is 980. A1 into H square. 600 into 40. A1 into H square. H is 980. 600 into 40 into 980 square. There are two flanges, therefore multiplied by 2. So it is coming to 49 mm and that is less than 83 mm. Therefore, this allowable deflection, this 49 mm deflection is less than 83 mm. Therefore, it is safe. Here, 10 power 3 is missing. 5 by 384, 88 kilonewton load per meter, kilonewton. For kilonewton to newton, you have to multiply by 10 power 3 here. All other units are consistent. 5 by 384, WL power 4. This is in millimeter, no problem, 25,000. 2 into 10 power 5, Newton per millimeter square, no problem. This is in millimeter power 4, no problem. This should be 88 into 10 power 3. Here 10 power 3 is missing. Please take care of this note. You should have here 88 into 10 power 3 into 25,000 power 4. In the numerator, 10 power 3 is missing. However, the value of deflection is 48.9 mm. It is less than 83 mm. With this, the design is over. We have assumed the cross section and then we have checked it for bending strength, shear strength, bearing strength, and deflection also. With this, the design of plate girder is complete. 1 second. I am requesting you to visit my website https://rgnsite.wordpress.com. My website is https://rgnsite.wordpress.com. Here many blog materials are available on structural engineering subjects like RCC design, steel design, structural engineering for diploma course, strength of materials, structural analysis part 1, structural analysis part 2, including matrix methods, global reflection method, moment distribution method, strain energy method, calculation of deflections, etc. On matrix methods alone, about 25 university questions and answers are there. In totality, on various structural engineering subjects, on RCC design, steel design, strength of materials, structural analysis, part 1 and part 2, in totality, there are about 500 university questions and answers. The download is free, including the design of plate girder, which we have discussed just now. All the university questions and answers, all the 500 university questions and answers are available in this blog site. The plate girder, the design of plate girder, which we have discussed just now, is also available in this blog site. The download is free. The download is free. There are about 500 used questions and answers. Please visit my blog. Thank you all for your passion listening.